So here's another example involving field extensions. This time we're looking at the rationals adjoined I and the cube root of 2. So this is the smallest field that contains the rationals and these two algebraic numbers. I'm looking at that and considering it a vector space over the rationals. And the theorem that we've been thinking about says the following. So let's break this down and see what things are saying here. This number, all the way on the right, is equal to 3. That's because a basis for the vector space q adjoined 2 to the cube root over q is 1, 2 to the 1/3 power, and 2 to the 2/3 power. That's because the minimal polynomial is x to the 3rd minus 2. That's a polynomial with rational coefficients that is irreducible and contains 2 to the 1/3 as a root. So that's my minimal polynomial. So I have 3 elements in my basis, so this number is 3. Every element in this vector space, every element in this field extension is a linear combination of these 3 numbers. Now, no linear combination where the coefficients are rational of these 3 numbers has a complex imaginary component. So I is certainly not in this field. So I is not an element in this field. So then I could think about the field extension by considering minimal polynomials. This number here is 2. A basis for this larger field over the smaller field is 1 and I, and that's it. Because a minimal polynomial is x squared plus 1. This polynomial has coefficients in this field, q adjoined 2 to the 1/3 power. I just didn't need to use any 2 to the 1/3 powers, or I guess 2 to the 2/3 powers in my coefficients, but still, the coefficients I think of as being in this smaller field. So this is a minimal polynomial. Therefore, a basis is 1 and I. There are 2 elements in my basis, so this is 2. Therefore, we know this is 6. And a basis is 1, 2 to the 1/3, 2 to the 2/3, I, 2 to the 1/3 I, and 2 to the 2/3 I. So these are the 6 basis elements, and I just figured them out by combining the basis elements in this situation with the basis elements in this situation. I did all possible products. That was how we proved the theorem that said this statement was true. Okay, I'd like to prove another theorem, a quick one, and then do a final example using this idea. So here's the theorem. So let beta be in F adjoined alpha, where alpha is algebraic of degree n over F. And suppose beta well, we know from a previous theorem that beta is algebraic. We proved that when you're looking at a field extension of this form where alpha is algebraic, every element is additionally algebraic. You can't have a transcendental element, beta, in this field over F. So beta is algebraic, but let's suppose beta is algebraic of degree m over f. So the theorem says m divides n. Okay, this proof is really easy. It's based on this result we have up here. The beta element is in the field F adjoined alpha, and therefore the smallest field that contains F and beta is contained within the smallest field that contains F and alpha. Therefore, we use our main result about finite extensions, and we have that F adjoined alpha over F is equal to F adjoined alpha, parentheses or brackets, doesn't matter here, over F adjoined beta times F adjoined beta over F. Now this, by hypothesis, is n. And this, by hypothesis, is m. There, that's the end of the proof. M times some integer equals n. That means m has to divide n. So that's the proof of the theorem. If you look back up at this theorem applied to the previous example, the minimal polynomial here was degree 3. So this was a degree 3. That means since I has degree 2, I could not have been contained in this field. All right, let's do another example to finish up the video. So let I be a root of the polynomial x squared plus 1, but this time I'm going to think of this polynomial as being in z3x. So I is going to be a root of this polynomial. This polynomial has no roots in z3 and it's irreducible. You could just verify that if you plug in 0, 1, and 2 into this value, you don't get 0 mod 3. So here is the minimal polynomial for I, and I'm going to say let alpha be a root of the irreducible polynomial 2x cubed plus x plus 1, and that again will be in z3x. So this is an irreducible polynomial. You could check it also has no roots in z3 and therefore irreducible over z3. I'm going to let alpha be a root of this. So then what we see is z3 adjoined both of these elements over z3 should equal z3 adjoined both of these elements over z3 adjoined just I, let's say. And this will be times z3 adjoined I over z3. Now, this right here is equal to 2 because the minimal polynomial here is degree 2. And a basis is 1 and I for this vector space over z3. Now, for this next one here, here's the situation. I have a minimal polynomial for alpha over z3. So I need to make sure, however, that if I'm allowing myself coefficients involving I can't necessarily factor this. So I know this, again, what I'm saying is this polynomial is irreducible over z3, but is it also irreducible over Z3 adjoined I, this larger field. Maybe because I have a larger field, I could factor this one now into a smaller polynomial. Well, it turns out you can't because of this previous theorem. So alpha is algebraic of degree 3. So that means this alpha cannot be, so by the theorem, let me write this down. By the previous theorem, alpha is not in Z3I. That's because I has degree 2, alpha degree 3, and 3 does not divide 2. So not in there. Not in there. That means this is the minimal polynomial. That means this thing is equal to 3, and therefore this here is equal to 6. Okay, great. I'll see you for the next video.